Hello friends, welcome to Civil Ideas. Today in this lecture, I will tell you about the stress strain graph of a ductile material. So, without any further delay, let's get started. Stress strain graph. Stress strain diagram is drawn with the help of an UTM universal testing machine. As we know, stress is equal to load by area. Here, area is constant and it is called as engineering stress. So, when you pull a ductile body, then the cross-sectional area of the material will decrease and it will become thin and the body will elongate. I mean to say, if the dia of this material is D, and after the tensile force is applied on this material, the dia of the material will change. It will become thinner. Now, the true stress is defined as, it is same as engineering stress, is load upon area. The true stress, the cross-sectional area keeps on reducing, and these types of stress corresponding to the instantaneous value of area is called true stress. Now, look into this stress strain diagram. Here, from O to A is bear is entirely linear. I mean to say, when the load is applied, then the stress is directly proportional to strain. Now, here the A dash is called the proportionality limit. Now, until point A, the stress is directly proportional to strain up to here, from O to A. From point, but it is not the elastic limit. From point A is the elastic, it means elasticity of the material will finish. From here, the elasticity of the material will be there. After point A, it will finish. The region between the point A will not be entirely linear. It will be bit curve. From here, this point, these 2 points, it will be bit curve. It won't be linear. If you remove the load from point B, here is the point B. If you remove the load, then the left region, means I mean to say this region, this whole region is called elastic region. Now here, if you increase the load beyond B, now simultaneously the load is increasing, then the region B is called plastic region. Now we enter this plastic. Here it is elastic and the right side is plastic region. If you remove the load from point C, then the strain falls. There will be a, from here the strain will be falls like this. There will be a strain OD. This line is called OD. Then there will be a permanent deformation of the ductile material. Now at point B, the permanent deformation starts and yielding starts. This point is called upper yield point, this point B. Now in the strain hardening region, the material becomes hard due to excessive strain. This is the strain hardening region. As you can see in this diagram, this whole diagram is the strain hardening region. The material becomes hard due to excessive stress. Now at point D, this is the point D, is the maximum stress on the body can produce to counter the deformation. Now this is the maximum stress. As you can see, this is the ultimate stress. Here it is written the ultimate stress. This is the maximum stress the body can take. Till point D, the material is hard, and beyond point D, the material starts soft, means it loses its plasticity nature and it's getting weaker. At point D, the phenomenon is called necking. Now before necking starts at point D, we start reducing the load, then engineering stresses reduces. That's why dipping occurs. I mean to say, means at the time of at point D, when the load is decreases, slowly its stress decreases. Since the necking occurs and the cross-sectional area of the material decreases, and we know stress is inversely proportional to the cross-sectional area. As area decreases, the stress automatically will increase. Now this position is called as true stress. Now this is engineering stress and this is called true stress. Now the difference between the engineering stress and true stress is that when the load at after point D reduces, then the necking occurs. Due to necking occurs, is shown in the graph, but when the load is slowly decreasing, the stress will simultaneously bit increase in true stress, because the cross section area of the ductile metal decrease, due to which stress is zero. As we know, stress is equal to load upon area. Now stress is inversely proportional to 1 by area. I mean to say, if the area decreases, automatically the stress will increase. Thank you.